Good afternoon and welcome back to the second webinar of INSPYRE, the International School of Modern Physics and Research. I remind to all the students that if you wish, you can participate in the INSPYRE 2022 contest. Share your INSPYRE experience with us. We would be glad to receive your feedbacks and insights you can realize and send us via email short videos, presentations, articles, comics, drawings related to one or more topics that interested you the more during this call. The three best products will be awarded with special INSPYRE gadgets. Let's come to the second webinar of today. We will talk about exotic atoms with Catalina Curceanu. Catalina Curceanu is a senior researcher at the Frascati National Laboratory, where she is leading a group of researchers performing advanced experiments in nuclear physics and quantum mechanics. She has received several awards and prizes, among which an award from the John Templeton Foundation and the Foundational Question Institute for projects on quantum mechanics. As usual, you can write your questions in the chat, and there will be periods during the talk to answer them. Catalina, the floor is yours.
Thank you very much, Susanna, and welcome back to the second day of International School. So good afternoon, Domenico. You are the first one to greet, so I will greet you back. Domenico, welcome, and nice to see you back with us. As Susanna was mentioning, I will tell you something about research we are doing here exactly in Frascati, actually at an accelerator which is quite near my office where I'm talking to you now. Hello, Paolo, and hello, Davide, and hello, Stella. Nice to see you with us this afternoon. And again, if you wish, just write me where you are now and where you are writing from, which country, which city. So every now and then, hello, Arianna. Every now and then I will come back and look at the chat, but now I'll go back to my presentation. Super great. So guys, here we are. So I told you that I am just near this particle accelerator, which is called DAFNE. And this title, which looks a bit crazy, all in a timble, I'll try to justify it and to give you a reason of this title and also of the research I'm doing together with my group in this beautiful particle collider, which you can see here after a rainy day. That's the machine, our collider, seen in a beautiful light after the rain. Also, there is here a picture from inside the DAFNE Collider, which is very colorful. So it's actually, I'll come back to this. It's a collider which is putting together matter and antimatter. And oh my God, meantime, Riccardo, Ambra, Eleonora, Ilaria, Francesco, Matteo, Martina, and Starking, nice to see you back, and hello to every one of you guys. Good. So I told you that this is a rather complicated machine which contains actually many accelerator components. I'm trying also to give you a kind of a very quick overview of what an accelerator is doing. Actually, in our case, that's a simplified version where you don't see all this mess, including vacuum pumps and all the electric elements of the machine and the magnets. You see here a simplified version, a sketch version, where actually it's explained what the machine is doing. Actually, it's colliding electrons and positrons, which circulate in two different rings, and they collide in a region, in a so-called interaction region, where they generate the so-called phi particle after the collision, and this phi particle decays in so-called kaons, which we use for our research. I'll come back to this. That's only a brief introduction to what we are doing together with my team, which we are called Siddhartha team. And the first experiment we installed already 3 years ago. It's Siddhartino, which is, let's say, the small version of the Siddhartha experiment, with which we already took some data in this collider. And yeah, so you see here, I also want to comment, since you are from many countries, that experimental physics, actually, it's very attractive also from cultural point of view, because in this picture you already see people coming from Poland, Hungary, half Italian, Austria, Romania, and Italy. And beyond this, in the collaboration, we have people coming from Japan, from Germany. So it's very exciting to be all together in the same aim and try to do research at best and try to discover something. What we try to discover are processes, which I'm going to tell you about. Meantime, let me hello Verona, Michele, Chiara, Samuele, Andrei Kalin. I imagine you are from Romania. Hello, Martino, Matteo. And then I'll try to answer you, Paolo. If you ask me what's my favorite camp in physics, I'll answer you after my talk. If you want to put questions, just ask questions in the chat and I'll try to answer as much as possible. So I'll try to explain you how we use our accelerator also to learn something about the stars. Not any type of star, but a very peculiar type of star in our case. And the stars are really fascinating objects. I remember I chose to study physics because I was fascinated by the stars, look at them, and was always wondering how far they are and how can we measure how far they are and why they are lightening, what's the source inside which keeps the star shining. And that's one of the reasons for which I chose to study physics when I was about 10, 12 years old. Now I do part of this research which explains what happens inside a star by the use of accelerator. Our own sun, it's a star, but that's of course not the only one. There are billions and billions of stars, including some of them, the ones which we are searching on, at least in our experiment. We try to understand part of the physics inside a peculiar type of star, namely the neutron stars, which can present sometimes under the shape of a pulsar, which emits a lot of energy due to the very intense magnetic field. So probably some of you, those who are passionate about stars, know that a star, it's a very complicated object and it maintains its equilibrium, so it doesn't explode or implode, which means that it is quite stable object for quite long period of time, which means long means billions of years for a star like ours. Much shorter if the star is bigger, and much longer if the star is smaller, due to an equilibrium of two types of very different in origin forces or interaction. One which is it's at work inside the star, which are the nuclear reaction, nuclear fusion of smaller nuclei like hydrogen, which are putting together, I'll show you in a moment, towards bigger and bigger nuclei. And in this reaction, there is a lot of energy. It's like kind of a nuclear bomb, which would like to make the star exploding, fading away. But there is another interaction which is actually opposing this explosion, namely the gravity, which quite the contrary would have the, would like to shrink the star potentially to a black hole. As long as this equilibrium is fixed, the star survives. So a star maintains its shape and it looks like nothing happens there, but actually everything happens there. In the heart of the star, there are nuclear reaction. Above, on top of that, there is gravity, which opposes, which does not allow it to explode. So that refined equilibrium, it's actually what maintains a star alive. And in this very moment, there are tons and tons of hydrogen burning. Actually, burning means undergoing nuclear reactions like fusion, nuclear fusion in the heart of our own sun. And the sun still does not explode because there is the gravity pulling, which opposes to the pressure induced by the nuclear reaction. That's the type of nuclear reaction. So two protons go together, form a bigger nucleus, the deuteron, proton and neutron, which adding to another proton forms another nucleus, which is in this type a nucleus of helium, and another helium they put together and they form a stable helium-4 nucleus, and so on and so forth. So that's how from light elements like hydrogen, you go towards heavier and heavier ones. Not all the stars are going up to iron, only the very big ones. Some other one end up at around carbon, so they are not able to go with the nuclear fusion up to iron. But when the star ends up forming all these heavier nuclei, it happens that the star does not have anymore an interaction which opposes gravity. So when we reach here and where the nucleus, the light nuclei inside the star formed heavier nuclei like the one you might see here, this is the case of a big star where you burn up to iron, then there is nothing to oppose gravity any longer. There is nothing to make nuclear reactions anymore, nuclear fusion. And this is the very last moment of the star life, when it ends its life in a big explosion. And actually, the fate of a star depends on how big it is. For big stars, like the one with the mass about 10 times or bigger than our sun, the end is really very spectacular. It delivers a supernova, so when it doesn't succeed to oppose gravity anymore, because there is no nuclear fusion inside to oppose the gravity, there is a gravitational collapse. And this gravitational collapse due exactly to the fact that these layers in a star have different densities. When it collapses, the layers collapse with different speeds. So they hit each other and part of the material explodes. And it's spread all around the universe and produces a big and shiny explosion like a supernova, but not all the material is spread around. There is a core, a heart of the star, which is undergoing still the gravitational collapse. And if the star is very, very big, this collapse does not end and forms a black hole. Quite the contrary, if the star is bigger than the sun, but not much, much bigger, what happens that the remnant, if the remnant is kind of smaller than 2-3 times the solar mass, forms a neutron star. And this explosion is quite spectacular, and it spreads in the universe the chemical elements heavier than those which formed after Big Bang, hydrogen and helium. And I will speak more about the neutron stars, because these are the type of stars we can somehow study in our collider by the experiment, which is Siddhartha, we are doing here in Frascati at DAFNE. We try to understand how this type of star is done. So as I was telling you, the remnants of the supernova, which it's exploding, spreading around material, chemical elements like carbon, iron, sulfur, and oxygen, and so on around the universe with very high speed, quite a fraction of the speed of light. And well, actually, we still have some remnants, and we can still see some clouds and dust, even of the last supernova seen in our galaxy, the supernova 1987A. By the way, if you wonder how many supernovae are exploding in our galaxy, the mean value is something like 3 per century. So we don't expect more than 3 in a century in our own galaxy. And that's why it is quite a spectacular phenomena which worth to be observed. And sometimes when the star it's exploding, as I was telling you, if the mass of the star is not much bigger than the sun, like 10 times, but not more than 10 times the mass of the sun, what remains after big part of material was spread in the universe shrinks, does not form a black hole, but forms what it is called a neutron star. Now, don't believe that neutron star is necessarily formed out of the neutrons, because that's one of the views, and that's what we believed up to recently. Now I will try to tell you why recent days this is challenged, and how we are trying to go beyond this simplistic scenario in which a neutron star would actually be a huge, like an atomic nucleus, but instead of having 100 nucleons, has 10 to the power 57 nucleons, all of them being neutrons. That would be in the simplistic version, the image of a neutron star, but it might not be like that. And that's what we are studying. And neutron star we see sometimes as pulsars, because there is a very, in this case, the magnetic field, it's extremely intense. So there is an intense magnetic field which streams radiation along the direction of the rotation of the star, which, if we are lucky enough to be in the direction of this beam of light, we see it, the beam of light turning toward us, we see it, and we call it a pulsar. And by the way, we are, when you hear, it's not only a metaphor when you hear saying that we are the sons and daughters of stars. It's true, because the elements, chemical elements beyond hydrogen, carbon, nitrogen, oxygen, sulfur, phosphorus, which are in our bodies, are born in the stars. So they are formed exactly in the reaction I told you, in the process of keeping the star alive while the nuclear fusion was acting to oppose gravity. So we are exactly formed, our body is formed inside the star, whatever it's beyond hydrogen. And the first pulsar which has been seen ever was in 1967, this emission of radiation, which was coming like a surprise by that time. So it's kind of beep, beep, every 1.3 seconds, a pulse long 0.04 seconds, so very short with this frequency, and very stable. So much that people for a while were even joking that it might be someone there who tries to communicate with us. Was not immediately obvious that that's a natural phenomenon connected with a star like a pulsar, namely a neutron star with such an intense magnetic field, which came quite immediately as a natural explanation, without bothering the existence of some other creatures which are trying to communicate with us with this type of radiation. Now, what about a neutron star? So, as an object, it's extremely fascinating, because the mass of a neutron star, it's about 2 times the mass of our sun, so twice the sun mass. But the radius, it's about 10 kilometers. So you have here a kind of an example of the dimension, taking, let's say, Vancouver as an example, and the neutron star about Vancouver. So it's really shocking to imagine that a star with a radius of 10 kilometers, which is nothing, would have a mass twice the mass of a sun. Of course, that if the dimensions are so small and the mass is so big, the density by definition is enormous. The density is so high that it would correspond to all of us, all humans on Earth, or nearly 8 billion of people, as if squeezed in a timble. So to reach that density, and that's the title that explains the title, all in a timble, because in this case, the density is equivalent to the one we would receive if I would give a party and I would invite all the people on the earth to reach me for the party inside a timble. So an extreme density. And at this density, of course, which actually, by the way, if you compare the density of a neutron star with the one expected from a black hole, it's not so far away. So it's only in radius about twice bigger. And of course, the volume goes with the square. But just to tell you that studying a neutron star and neutron star's gravity might also give a hint of bring us on the threshold of a black hole, which is complete mystery. So the study of neutron stars, it's extremely fascinating. And as I was telling you, up to, well, some years ago, people and scientists believed that the neutron star is made of neutrons squeezed one on top of the other, on top of the other. So huge ball, huge in the sense which compared to the atomic nucleus. So 10 kilometers radius of neutrons squeezed one near the other one. But quite recently, this has been challenged by a series of discoveries. And right now, it's not so clear that a neutron star is made out of only neutrons. One of the possibilities is in the heart of a neutron star, there is matter under a form which is quite exotic. So the inner core of a neutron star might contain, these are the various type of hypotheses. So you see, one of them is that a neutron star, it's containing only neutrons. So this is, it's neutron plus some residuals of protons and electrons, but basically it's mostly neutron. But there are more exotic versions, like one which says that actually a neutron star might have inside the core particles which contain the strange quark under the form of kaons, or even melted down in the form of a quark melting stars, so kind of a quark glue ball inside the heart of the star. The key word here is the strangeness. So go beyond the quarks which compose protons and neutrons and go to the second family, namely the strange quarks. And this is what we are actually studying. That's our contribute. By the way, as a second curiosity, let me tell you that there are mountains on a neutron star. But a mountain on a neutron star has kind of an atomic dimension. So you can't expect on a neutron star like Everest, 8 kilometers tall. The mountains on neutron star are microns or even less. So they are microscopic mountains, but even this type of non-uniformities might have dramatic consequences when you study this type of objects, especially considering that they rotate with a speed which makes a full rotation in a millisecond. So that's quite interesting. So what I was telling you, we try to go beyond the normal matter, beyond what it's contained inside the atomic nucleus. That's how an atom is made of. And we all know that atoms contains protons and neutrons in their nuclei. And in turn, protons and neutrons are made of quarks. And actually, inside the neutrons and protons, there are only two types of quarks, up and down. And in the proton, there are two up quarks and one down, while in the neutron, the opposite, two down quarks and an up quark. So you see that even the helium nucleus, it's quite complicated. Actually, that's the atom. When you go to study its composition in terms of elementary particles like quarks and gluons. But beyond that, we have an entire zoo of particles. So there are not only the particles which compose the present atoms, but so these are the quarks which are inside the atomic nucleus, up and down. Beyond that, in the particle accelerators, that's an interesting story, fascinating, but I don't have time to explain it. Other type of quarks were discovered, four others: the strange, the charm, the top, and the bottom, which are composing particles which, at least for what we know up to now, live very shortly and in the end decay towards particles which are stable and contain up and down quarks. That's how, what I told you before, how an atom is composed. So when we study the atom structure, we discover the nucleus, which is composed of proton and neutrons containing quarks, and the electron orbiting around the atomic nuclei. And when we put all together, we obtain what it is called a standard model of elementary particles, which contains all those particles which we call exactly elementary. I see a question about the spin. So the spin-off particles, it's half integer, so 1/2 for the matter particles, which means quarks and leptons, and it's entire spin, so they are bosons for what regards the interaction mediator, like gluons and photons and Z particles. So these are entire, and this is half entire spin, 1/2. And the last right is the Higgs boson, which was discovered. Actually, we are celebrating this year, which was discovered 10 years ago at CERN. So it's quite a recent discovery. You were born by that time. You might not have been born when TOP was discovered in 97 last century, but definitely you were born when the Higgs boson was discovered 10 years ago. Now, the issue here is that we study, so as you see, normal matter, it's composed only out of particles from the so-called first family, up and down, electron, and that's it. But there are families like the second one, which contains the strange quark, which might not play a role in stable matter on Earth, but might play a role in stable matter in the heart of a neutron star. And that's what we try to discover in our experiment. So matter, stable matter beyond what we have on Earth. And how we want to discover this? Well, what tells you, I see a question from Samuele. He asked me why in this case the Higgs boson is put aside. Well, because the Higgs boson really plays a role which is quite different from all the other particles. First of all, it's a particle which is at the bottom of the mass of all the other particles. So it's quite different than the others. It's the mediator of a field, actually is the representative of a field of energy, which gives the mass to all other particles. And the Higgs boson is the representative of this field of energy, which is all over the universe, which through what is called the Higgs mechanism gives the mass of all particles. And as such, it's not involved in any, let's say, individual interaction like electromagnetic. It's not explicitly and directly involved in the electromagnetic interaction or nuclear strong and weak interaction, but it's beyond this. It's more important because it was giving mass to all the other particles. Good. I see your question, Paolo, but I don't want to answer to you now because this would bring me a bit out of what I want to tell you. Okay, so the temperature of a neutron star, it's actually not so high. So it's not extremely hot matter. It's called cold and dense matter, quite opposite to what we are doing at Large Hadron Collider, where by colliding nuclei, we do the so-called hot and dense matter. The neutron star, it's formed in quite a cold, let's say, remnants after the explosion. So it gets colder and colder, and it's cooling down as time is passing. So it's not very warm, it's cooling down. So we are focusing on this strange particle, strange quark, and what tells you whether you can form stable form of strange matter wherever, including inside a heart of a neutron star. What makes it stable is the strength of its interaction with the normal matter. So let me stop a bit here. So if the quark, the strange quark, some way interacts with the other quarks up and down inside the heart of a neutron star extremely, extremely strongly, forming extremely bound, so deeply bound states, this would stabilize the strange quark, quite opposite to what happens with this quark when it's free of everything, then it decays. So it would bring the quark, it would stabilize it if the interaction with the others, it's so strong as to bring it in the form of deeply bound matter. So the strength of the interaction is the one which gives indications whether the interaction of this quark is strong enough to can imagine that it forms, stable form of matter inside a neutron star. So what we want to do in our experiment is to measure prototypes of this interaction, so how strongly particles which are composed of strange quark interacts with other type of matter which is containing only up and down quarks, and check whether this interaction is strong enough, so provide this our measurement to theoreticians which are using our data to extrapolate towards the conditions of density which is inside the neutron stars. So we are trying to measure a kind of a extreme prototype of neutron stars, so kind of a proton and a kaon, a particle containing the strange quark, or even more complex interaction, and to measure them, provide our data to theoretician, and then they can try to use it and measure whether the calculations tell whether this it's kind of favors the possible existence of stable form of strange matter inside the heart of neutron stars. How we do that? Well, first of all, we need to have particles with the strange quark inside. And since you don't buy it at the supermarket, we need to produce it. And we produce it through collisions of electrons and positrons, which are providing, let's say, particles in the final state. So we collide electrons and positrons, and we create other particles in the final state. And what particles we can create in the collisions, it's decided by the energy we put inside the beams. So we can select what we want to produce in our collider by selecting the energy of the initial beams of particles, because what we rely upon, it's this famous Einstein formula, when we can select what is the mass of the particles we want to have in the final state, then we know what is the energy of the electrons and positron beams we want to collide in order to generate the particles we want to have in the final state. And by itself, this method of colliding electrons and positrons, for the first time in the history of physics, was, by the way, realized exactly here in Frascati, in all the world. So this was the first place in the world, which now became the historical site of European Society of Physics. We still have this, and I hope that some of you who would come here either as colleagues or as visitors might see it. We have it right now in our open museum, open air museum, the original ADA machine, which realized the very first collisions in the world of this type of particles. We then had a first accelerator from the end of 60s up to 93, and right now we have this beautiful machine since 97, which is called DAFNE, where we realize these collisions, electrons and positrons, to deliver. That's another picture of the machine, and I'm really, really sorry you are not here with us so you can see and touch in person, but I hope you will come here one day. That I already show you this picture with these magnets. That's another picture from above of the same machine. And that's, again, briefly the history, which tells you what I told you before. And let me tell you that now the same technique, it's used all over the world where there are particles colliders. Also at CERN was used, and it's being used at this Large Hadron Collider machine, where beams are collided to generate, through the Einstein formula of equivalence between energy and mass, particles in the final state, and study whatever you want to study, dark matter, or, as in our case, strangeness physics. Accelerators work with electric and magnetic fields. Electric fields are accelerating, and magnetic fields are changing the trajectory of the particles, shaping them to go, for example, in a circle. And we do this to create and study interactions of particles which are not stable in the universe, but we need to study them using these beautiful machines, which are actually bringing us to a threshold of new discoveries. So let me tell you what type of physics we are studying in our accelerator, which is called DAFNE. Well, in our case, the energies of the beam, it's tuned such as to form after the collision through the annihilation of the electron with positron, the so-called phi particle. We are not necessarily interested in this phi particle. We use it because it decays quite immediately. Its lifetime is something like 10 to minus 20 seconds, and it decays in these two back-to-back so-called kaons. And what we are interested in is this negatively charged kaon. This negatively charged kaon, quite opposite to the proton and neutron, which are built only out of up and down quarks, it's built up of a quark and an antiquark, and one of them, it's what we are caring about, the strange quark. So that's how we produce the strangeness under the form of the negatively charged kaon to our machine. And that's the unique machine in the world where this process is undergoing, producing ideally strangeness under form of kaons, which we study to create different type of atoms. So you know that usually an atom is a nucleus surrounded by electrons. And you study, for example, what you can do with an atom. You can do atomic spectroscopy. What does it mean? It means that you can study the radiation emitted in the transitions of electrons from one energy level to another. When this happens, there is an emission of an energy, and by measuring this energy, you can actually measure the energy of the atomic levels. So you can do spectroscopy and you can exactly characterize the energy levels in a normal atom. We do the same, but not with normal atoms. We do exactly the same, replacing what it is the electron with this negatively charged kaon. So let me see what I put here. Okay, so let me show you first this. So we use the kaons which are formed in the DAFNE machine to actually to put them inside a target which we want to form kaonic atoms. The kaon is replacing the electron, it's 1,000 times heavier. So when it approaches the electron, it kicks the electron out from the atomic orbit and it forms with the nucleus a so-called exotic atom. It's one of the types of possible exotic atoms. In this case, it's a kaonic atom for obvious reasons. But since the kaon is much heavier than the electron, once it positioned itself at a distance from the nucleus at which the initial electron was, the electron replaced, it finds itself in a very highly excited level, very highly excited from the energy point of view. And the kaon starts to do atomic transitions coming towards the fundamental level. In this atomic transition, it emits radiation like X-rays. By the way, that's exactly what we measure. We do spectroscopy, but not of a normal atom, of a kaonic atom. What is the goal to do this type of spectroscopy? So what's the point in all this? The point is that when the kaon de-excites and when it comes so close to the nucleus, by the way, a kaonic atom is much smaller in dimension than a normal atom. It's like a kind of very, very teeny, teeny atom with respect to the original dimension of, let's say, the normal atom, which it's replaced, where it's replaced the electron. Now, when the kaon comes near the nucleus, differently from the electron, it interacts with the nucleus, yes, through the electromagnetic interaction, because one is positive, the other is negative. But on the top of this, since differently than electron, the kaon is composed of quarks, like the nucleus, there is also a part of interaction which is due to the strong interaction. So there is overimposed on the electromagnetic interaction, there is a contribution from the strong interaction between the kaon and the nucleus. And that's exactly what we want to measure. How strong is the strong interaction between the kaon and the nucleus. So it's like a kind of Trojan horse which helps us to disentangle the contribution of the strong interaction between the kaon and the nucleus if we measure the energy of the X-ray. Why? And let me go before, because in this, these are the energy levels in the kaonic atoms, and with respect to the electromagnetic calculated energy, we measure a difference. And this difference which we measure, it's due to the strong interaction between the strange quark and the, well, between the kaon and the nuclei, between the normal matter. And that's what we want to obtain. The strong interaction, namely the strong component of the interaction, which is due to the embracement between the kaon and the nucleus. So that's a very clever method which helps us to disentangle the strong interaction when we measure the X-ray radiation, and when we subtract from what we measure the part due only to the electromagnetic interaction, what we remain it's what it is due entirely to the strong interaction between the kaon and the nucleus. And that's exactly what I'm aiming for, because the strength of this interaction, which I provide to theoreticians, they use to say something about the possibility that a neutron star is hosting in its heart kaons or strange type of matter. And that's how we do it. So I show you a very brief kind of a sketch where we have electrons and positrons forming 5 decaying kaons. Negative kaon is stopped inside the target, forms kaonic atoms, which decay, delivering X-rays, which are measured by X-ray detectors. And here are some, these are the pictures of our X-ray detectors. We use silicon drift detectors, which are quite, let's say, quite sophisticated. So they are like the detectors in our digital camera, which make imaging. They are CMOS detector and they measure light. In this case, we use detectors to measure much heavier light, let's say, so much more energetic light, the X-rays, which have energy with respect to visible light kind of 1,000 times more. So silicon drift detectors, which are surrounding a target where we put what we want to study. And of course, we study with the simplest nuclei like hydrogen and deuterium. And we measure this transition. That's a bit how it looks like, the X-ray detectors surrounding the container of the target. And that's again the group 3 years ago when we started to install our apparatus inside accelerator. Then unfortunately we ran into the COVID and we restarted pretty recently. So we restarted, this is our collaboration. Siddhartha in this case come from silicon drift detector for hadronic atom research by timing application. And this is a collaboration which I already mentioned. It's highly international, and that's part of the charm to perform experiments in the international environment, because you interact with people coming from many places, so you have also cultural exchange. That's a bonus to do science. And that's the type of measurements we are aiming at, which means, let's say, which means type of spectroscopy. So when a physicist is telling you, I'm measuring something, usually what he or she, it's meaning, it's that we measure, let's say, a number of events, function of something, that's a histogram. And in our case, the histogram which we are aiming, it's number of events, function of the energy of the radiation of the X-rays, for example. And moreover, that's not a real measurement, that's a simulation. So that's what we expect to measure, but of course, until we don't do the measurement, we don't know its energy. So exactly what we want to measure, that's a fake energy we put inside. It's a simulation to see how is the spectrum we are expecting to measure, but we don't know where actually this will be. So that's the funny and exciting thing, that we expect to see events spread a bit around the energy, And what we are interested in is to measure exactly their energy. Would it be 7,000, 7.2, 6.4? So that's what we are eagerly awaiting to measure, not in 2019, but that was before COVID came. We were supposed to start by the end of 2019 and go through 2020, 2021. Now, this couldn't have been because of the COVID. Now we are starting the measurement right now. And this is interesting because you see, now disregard this red rectangle and look at the spread of what theoreticians are predicting. So if you ask theoretician, what you expect from our measurement? Well, you see that there is absolutely no agreement. Like, for example, in the position, so the strength of the interaction, it's absolutely not agreement. So there are somebody who says that shift is proportional to the strength of the interaction. Bigger is the shift, which means what you measure when you subtract the the purely electromagnetic interaction. So that's the strong interaction. So if you see somebody saying, no, the interaction is very strong. Others are saying, well, no, it's only 600 at something, not so strong. So there is absolutely no agreement among theoreticians. Now, our measurement, no, all measurements are done with a certain precision. So there is not a dot. You are having errors in measurements. Some are due to statistics, some are due to systematic errors. So that's what we are, our targeted precision. But of course, we don't know where it's going to be, here, or maybe here, or maybe here, or maybe where we put it here. So everybody's eagerly awaiting, theoreticians, us, to see where our measurement will stay and who is right and who is wrong in these predictions they have done along many years. You see, there are 20 years that people couldn't do this measurement, and that's something which is strongly awaited by scientific community. And this will also have an impact not only to say whether there could be some strangeness inside the neutron star, but the more exotic hypothesis, that's another fight within the community of people working on the neutron star. That's a fight which they say that there might even exist two types of different families of neutron stars. One which is containing melted quarks. So quarks wouldn't be confined inside neutrons or kaons or whatsoever, but would be completely melted, and it would be a blob, kind of a blob or a kind of a sphere where quarks are free inside under this kind of cold but high density matter, and they are quarreling among us, and they need to be fed with experimental data. Of course, not only ours. So ours, it's only part of the puzzle. There are many other experiments, including those at CERN, which are contributing to this puzzle. And this would go to complement information coming from other sources. Other sources like the gravitational waves, they are also giving information, complementary information in forms of gravitational waves about the structure of a neutron star. So the big dream in this concern is that we will be able to put together information coming from nuclear physics like ours with gravitational physics like people studying the gravitational wave, and have a more complete view. So these are the gravitational antenna, more complete view of these fascinating objects, which are predicted by general relativity and are confirming the general relativity of Einstein. But we might discover, and that's the hidden hope, that already at this level we might find some departures from general relativity, which are strongly needed if we want to explain what happens inside black hole. because neutron star can still be explained by general relativity. But a black hole where the general relativity goes to a singularity, meaning gravity goes to infinity, cannot be explained by general relativity. So we are even hoping that we might get some, let's say, signals of some departures from general relativity and be able one day also to contribute. That's, of course, it's a faraway goal, but to contribute to answer also to questions like what if I jump in a black hole? What can happen inside? So have a theory of what would be the gravity in this extreme condition, which for the moment we have not, at least not a confirmed one. Uh, so what would happen? A part of the fact that if we would be to jump into a black hole, better to choose one which is huge, because the small ones with solar masses are inducing the so-called spaghettification. The gravity is too intense. So better to jump into a huge massive hole if we want to be no spaghettificated, like the one which I quote here, NZC 1277, with a mass 17 billion times the sun mass, which is absolutely not dangerous to go into, but you can't go out, staying to present day physics. So yeah, alternatives is that you might jump somewhere else in the galaxy, so you might get a shortcut, extreme curvature of matter and of space and time, or even as we see here from this magician of black holes, he was saying that black holes are passage to other universes. And I end here with this very nice quote from Marie Curie. I was trying to give you an idea that what she says, that I am among those who think that science has great beauty. A scientist in his laboratory is not only a technician, he is also a child placed before natural phenomena which impress him like a fairy tale. And there are fairy tales in front of us everywhere. So you have heard before dark matter, you have heard before the day before physics, even a proton hides a mystery. I try to give you a hint about neutron stars everywhere, depends with which eye you are looking at them. But I think you are living, so you are kind of lucky, you are living in an amazing period where there are full type many mysteries, dark energy, dark matter, neutron star, gravity inside a dark black hole. So you're in the middle of many mysteries. So I think it's a great time to do science, not only physics but all type of science. It's really a great time to do science. So what I can tell you here, it's okay, beyond us acknowledging all my financing projects going from European Strong 2020 and to American John Templeton Foundation, FQXI, and all those you can see here, I can strongly tell you that physics is really an amazing adventure. It brings you far, it brings you to travel, it brings you to enjoy. Like every time somebody asks me, are you going to work? I stay a bit like that and say, to work? No, I go to enjoy, I go to do my hobby. So if you want to do science, girls and boys, just go for it. It's amazing. You get paid for it, to travel, meet people, and after all, play with beautiful things. So thank you very, very much. And now Susanna, if you want to join me, I'm trying to answer questions.
Yes, Catalina, I'm here. So as far as I understood, you already answered some of them, right?
Yeah, I see from Marco a question which looks interesting. So he asked me, how do you know that the count is interacting with D quark or the U quark? Is it exactly the same interaction, or there is a way to distinguish the two kinds? That's a very clever question, Marco, because actually we cannot separate quarks. Quarks cannot be isolated. There is a complicated story. Quarks only live together. This is called confinement, has to do with properties of the strong interaction. So I cannot, unfortunately, study the separate interaction and take a strange quark and interact it with U or D. So I need to use the theory. So I have to use theoretical tools like the standard model to build up from what I measure, and my measurement is not the only one. I need to do other measurements with other particles to disentangle the separate interaction between U, S, and D quark. So you need to put together in the framework of a theory, which can be lattice QCD, or it can be chiral symmetry. Now, don't bother about the names, but there are tools, sometimes very complicated tools, theoretical tools, which are fed by our measurements, which can in the end disentangle the bare necessities, how you say, yeah, the bare interaction out of the experimental data when you complement them. Very clever. And that's you put the finger exactly in one of those very difficult issues in the nuclear physics, Marco. Now I see, quark and positron, Paolo, I cannot explain you. These are, just go and read something on Google them. That's what I can say. There are elementary particles which you easily can get information by Googling them. And now, Andrei, what you're asking me, you answer to Paolo that the
Paolo, yes.
positron is the antimatter equivalent. Good, guys.
Yeah,
Perfect. Interaction. Nice. What happens when black holes collide? Yeah, well, that's an interesting issue, because what we believe it happens, is they create a bigger big hole. So I have 30 masses, solar mass plus other 30, they collide, but be aware, they do not form a 60 solar mass black hole, because part of the mass is transformed in energy of gravitational wave. So my guess is that they might form 56, 57 only, because 3 solar mass are gone in gravitational waves. Robert Christian, how does the black hole affect the time? Wow. So the general relativity tells us that the time slows down when gravity is more and more intense. And we know that the black hole is the extreme of gravity, which means that from an external observer, if you, Robert, would go to a black hole, I would greet you and I would see you frozen. So for me, watching you would look like your time would never pass. You would be frozen in the last moment when you would cross the event horizon. For me, you would stay like that forever. So if you ever, Robert, go to cross the horizon, please smile to me, because that would be the last and forever image I would have from you. Not the same for you. For you, in your system of reference, you would pass through, and you would be disconnected from my universe. So once you are inside the black hole, your universe disconnects to mine. So that's a very interesting issue. And I hope, Robert, you might continue asking this question and go to study them. Nam, why does a massive black hole not cause spaghettification while a solar-sized black hole does? Good question. Because the gravity, so if you go and calculate, the calculations are not even very complicated, by the gravity at the event horizon, which means the last frontier, after which, if you cross it, you can't go back because you need higher speed than light. Susanna, maybe you can take away the slides so we can.
Yes, sure.
Okay, so I was answering to Nam. So yeah, the gravity at the horizon scales inverse proportionally to the mass. So the formula is not even very complicated. By the gravity goes like 1 over mass. 1 over mass, if the mass is small, means gravity is very high. So it's a simple calculation which brings you with the and the result that gravity is inverse proportionally 1 over the mass of the black hole. Huge black hole, gravity is small at the event horizon. So Marco, go to the nuclear physics. Okay. Yeah, Samuele, you're right. That's very nice. So spaghettification, moreover, that's a good adding to what I say. You'd get spaghettified anyway, but that's a very clever adding, Samuele, that spaghettification in the end, it's also generated by the fact that the gravitational pull between your leg and your head, there is already such a big difference between the two gravities. Also on Earth we have them, but in extremes of the black hole, they are so different that you are pulled by the legs much more than by the head. And if you think you're clever and you jump like that, so like when you go to the swimming pool, you won't be able to breathe nevertheless. So it's not a good idea to go. The gravity is really, really huge. Since when black holes exist? Well, Paolo, that's another interesting question. It's interesting because we are aware only about the fate of the black holes which are born out of the explosion of big stars. They form black holes with the mass tens of times of our sun. But this doesn't tell anything about necessary about the black holes in the center of galaxies, which are million or billion times of our sun. And there are some theories which are claiming that there might be black holes out there which might have been born after the Big Bang, out of quantum fluctuations immediately after the Big Bang. But there is no confirmation of that. And that's an interesting issue to be studied. There are many, many contradictory studies in this context. So since when we have black holes? Definitely when the big stars explode, but might not be the only source. Susanna, you want to pick up some question?
Yeah, the one from Marianna. What makes the difference in the process of creation of neutron stars from creation a star with three quarks and one with confined quarks?
Okay, Ariana, let me try to tell you that's a complicated calculation for which theoreticians are fighting. And if they would listen to me now, they probably would not agree. Not one, not the other one. I will tell you what I understood from them from the point of view of an experimentalist. So the key factor here is the radius of the neutron star, so the density. And as of today, the radius of neutron star, I told you 10 kilometers, but that's not well known. Actually, what we can say is that the radius is probably between 8 and 14 kilometers, 8 and 16. And you can imagine it's a factor 2. Factor 2 in radius goes in density like a factor 8. It goes like the volume. So it's nearly an order of magnitude difference in density. And since we do not know well the radius, there is full space to play with the density inside the neutron star. And this game with the density allows to make different type of calculations. And some of these calculations, which is nice because you see, guys, you already have done a team of researchers, because this connects very strongly to the question which Marco asked me before, the nuclear physics, how you study the interaction of quarks between them. And I told you there are complicated theories, complicated models, really complicated, which then are used within the neutron stars at the densities which are unknown within one order of magnitude difference. And from the interaction of quarks like up, down, and strange, you might end up like quarks need to be bound in neutrons, protons, and kaons, or they can be also free. And this is relying on the equation which Marco asked me about. So Marco and Adriana, you are already a team of researchers which go from the strong interaction between quarks up to the equation of states in neutron stars. Go for it. Yeah.
Pietro is asking which black holes can contain a wormhole if they exist.
Oh my God, to be honest, I can't answer to, also because the wormhole, it's not necessarily connected with a black hole. So the conditions to form a wormhole are quite are quite differently defined than a black hole. So you need in a wormhole, what you know is that you enter here and you go out here. While what happens in a black hole, it's unknown. And to form a wormhole, you need a special type of energy, at least as we can imagine now, this type of energy, which should contain some exotic type of energy, which is negative, as if negative mass. You would need a kind of a negative mass. And that's something which, for the moment, stays only in our kind of, let's say, imagination.
Then we have two questions connected to black holes. So the first one is, can black holes die? If not, how can the universe still exist even if with the presence of a growing number of black holes?
Very nice. So I see the question was asked by Morad Abu. Where are you, Morad? Just write me. I'm curious. Where are you? Where are you asking this question? Well, you know, you have put a very interesting question for which actually Stephen Hawking would have answered to you in the 70s. No, black holes are forever. In the 70s, however, he changed his mind. But he changed his mind not because he was a capricious person, but because he was a very clever physicist, in the sense that he realized that there is an effect which was called the Hawking radiation, which would make so that a black hole does not live forever. Okay, so you are from Rome. Hello. And the black hole does not live forever. There is a quantum effect, a very interesting and very, very, very beautiful effect, the Hawking radiation, which would bring in the end that a black hole is evaporating. So just look into Google it, Hawking radiation, and you would see that at least in principle, a black hole does not live forever. Now, how long it takes a black hole to evaporate, well, if the black hole are like those we see in the universe, I dare say nearly forever, because in order to evaporate, they shouldn't eat. They shouldn't eat anything. They should be fully isolated, and they eat always something. If not else, they eat the how it's called, the radiation, the background radiation, which permeates the universe. So, but Google it, Hawking radiation.
Elena is asking, can I survive if I fall into a black hole?
Yes, Elena. If you choose a huge black hole, from what we know today, so from our knowledge as of today, if you would go into the black hole, well, if you are not hit, so if the black hole is not in a kind of a very active environment, in the sense that together with you, it's not eating up thousands of stars, which are creating a kind of rocks which hit you before enter the black hole. But let's assume it's an isolated black hole with a mass billion times the solar mass. You can easily enter inside. The mean density is like the air. So you can go inside, nothing happens to you. You might not even realize you are inside the black hole, but you would never be able to go outside, to escape the huge gravity of the black hole, staying again to our knowledge as of today. So yeah, that's something which it's I repeat, it's our knowledge as of today, and maybe some of you will discover something which goes beyond that.
Okay, maybe the last question, is that okay for you, Catalina? And then we can conclude our session, okay? So how could the strange quark stars be observed?
Oh, Davide, that's a nice question, because in the end, what you wouldn't know it's a strange quark star because it does something specific. So Davide, you joined the team of Ariana and Marco. Now you are three. You were two, now you are three. Why I'm saying this? Because if you put together the nuclear physics of the quark interaction with the calculations that Ariana asked me about, in the end, what could happen is that you would know it's a strange quark star if you would be able to measure with extreme precision the radius of the star. So, and there are now missions, there are now satellites mission which are meant to measure the radius of the neutron star. If you be able to pin it down with extreme precision, like I know that it's 8 kilometers plus minus 100 meters and not as of today 10 plus minus 2 kilometers, then you'd know, because you'd combine the knowledge in the nuclear physics of quark interactions with the calculations inside the environment of the neutron star, and you'd know that that type of quark, bearing on the information of its mass and its radius, it's a quark star.
Okay, so thank you, Catalina. There are two more questions, but I guess we can answer even offline. So we can...
let me try to answer to at least two of them, because I don't want them to be disappointed. Which one?
Okay, so maybe it's possible that in the future the Earth will be eaten by a black hole.
Yeah, if a black hole creates in nearby vicinity of the Earth, which for the moment we are absolutely unaware of, so for the moment it looks like not, yes, it is possible if we are nearby, too near. For the moment we don't run that danger. There are no such black holes.
So black holes are associated with vacuum. So how does the excess vacuum or charge fed into the black holes manifest itself?
I don't understand what means black holes are associated with vacuum. Okay, maybe, okay, you maybe Googled the, I take for granted you Googled the Hawking radiation, because Hawking radiation it means that there are this type of quantum fluctuations in the quantum vacuum nearby the horizon. So what means the Hawking radiation? It's you have a black hole, and outside the black hole, but in the vicinity of the black hole horizon, let's say that's the black hole, and before entering the black hole, the vacuum in physics, it means boiling up particles and antiparticles. That's kind of quantum vacuum, and one of them falls inside the black hole. The other one becomes a real particle, but you can't have a real particle out of nothing, so it does it by eating up energy from the black hole. And that's how the energy of the black hole, in the end, it's eaten up by all these particles popping up from nearby the black hole horizon. So part of them are eaten and part of them become real, but to become real, you need to have energy extracted from the black hole. So that's how I interpret your question. Okay.
Okay, so I think we can conclude this afternoon session. Thank you, Catalina. Thank you to our students. Let me remind you that we will meet tomorrow at 3 p.m. On this playlist, and have a nice evening.
Thank you very much, Susanna. Thank you to all of you guys. I really hope some of you will choose science. Thank you.